Okay, so this is work that I did when I was at News UK recently. Collaboration between Dion and Tom, who are architects at News, myself and Carlos, who are contractors brought in for this project. And just an overview of what I'm going to talk about. Firstly, motivating the topic, so why you should be interested in recommendation engines, some related work, and a bit of background, but then some more details on the actual algorithms we're using and how we've evaluated them. And finally, I'll talk briefly about architecture, but it probably will be quite brief because I focus mainly on the algorithm side. Okay. So the kind of core of what we've done is about matrix factorization. How many people have either worked with recommendation engines or matrix factorization of some kind? Mm-hmm. Okay, quite a few. Cool. And it's really useful because it's about finding relationships between things. So in any situation where you need to find similar users or similar items based on how the people interact with things, it's really, really useful. And so some examples are recommending, so the kind of recommended items you get on Netflix or Amazon, but also things like word meaning similarity, so latent semantic analysis is one of the first applications of this kind of stuff. Personalized search, feature extraction, missing value estimation, so there's loads of things you can use this stuff for, so hopefully I can convince you that it's a useful thing. I should just say the reason I'm spending most of my time motivating this, by the way, is because my PhD supervisor always used to tell me that the purpose of an academic talk is not to get people to understand what you've done, because they probably won't 20 minutes. The purpose is to get people to want to understand it, or to enough to want to read the paper, essentially. So it's like an advertisement for reading the paper. So don't expect to understand everything, but hopefully you'll know enough to know whether you need to read the paper. So the algorithms that have been developed for matrix factorization are also very highly developed, and I think part of the reason for that goes back to the Netflix prize, where they offered $1 million, I think, for the best recommendation algorithm, and I think that kind of sparked a lot of interest in this area. So that's why you should be interested in it. Why we were interested in it at News UK. So this is specifically for the Times. So when I was brought on, it was initially just for the Times. Did anyone read the Times? You don't have to admit to it. It's fine. So the goal was to increase retention. So they had a lot of people that were subscribing but weren't reading very frequently. And with the Times, it's a paid subscription. So if we lose subscribers and we lose revenue, it's quite simple. So the goal was to try and get people to stay by saying, here's some interesting articles that maybe you should have a look at, and convince people that actually they shouldn't end their subscription. So particularly for the Sun, but also for the Times, we needed to be able to do this really at scale. And it was just being rolled out for the Sun when I left. But with the Sun, there's an additional problem that we not only have like an order of magnitude more users, but also an order of magnitude more articles being published. So that's a large part of what motivates the algorithm that we've developed here. And it needs to be very fast. So with the Times, we were just sending out an email once a day, and that was fine. But if it's actually going to go on the website, we need to be able to generate the recommendations very quickly. And when we looked at what existing algorithms and systems there were that could do this, we found that they weren't quite suitable. So the implementation that we initially built was using Spark, and we would do this matrix factorization once a day. It would take about 40 minutes. At the end of the day, we'd be able to give people their recommendations. But that's not going to work when you've got new articles coming in all the time throughout the day, and you need to be able to recommend them straight away. However, there are some people that have looked at how you can do online matrix factorization. So the stream ranking one is one example. However, the problem with this for us is that users and items must be specified in advance. And of course, we've got new users and new items, new articles all the time, so that was no good. Something called X streams, where you can have the users and items, but the algorithm they're using is not the kind of state-of-the-art matrix factorization algorithm that we'd really like to be using. And finally, there's a paper on the algorithm that YouTube use, which is a deep learning based one. However, in that paper, they don't really describe how they implement that to be real time. So that could potentially be useful, but we need to see more details on that. Okay, so this is the first algorithm we implemented. Well, it's not an algorithm. This is a Times article, and the first algorithm we implemented was just, I guess you'd call it something like learning to rank. So it was a logistic regression classifier trained off unigrams in the content. So this is the content of the article, the title, section, and the author. All those features would go in. And we trained it on articles that the user had read for more than 10 seconds, or they'd shared on it, or they'd commented on it. So those were considered like positive set for that user. And then the negative set was just a random set of articles. And we trained the logistic regression model on that, and given a new article, we would get a probability coming out of the logistic regression model, and we would take the highest ranked, we'd rank them and return the highest probability articles when we want to recommend an article. And it worked fairly well, but it didn't work as well as our other options. So if you're not familiar with matrix factorization, this is a kind of stupidly simple description of what it does. So these are your users down here, and these are your articles on the top here. And you basically put a 1 in the matrix if the user has had a significant interaction with that article, and otherwise you leave it as a 0. And the goal is to decompose this matrix into 2 much smaller matrices, where this dimensionality along here you get to choose. In this case, we've chosen 3 dimensions. And the number of dimensions kind of gives you a granularity of how descriptive your model is, if you like. So you end up with a matrix for users and a matrix for articles. And when you take the product of those, you get back an approximation to your original matrix. And it's important that it's an approximation, because what you're then going to do is look at the bits that get filled in here. Some of these zeros will no longer be 0, they'll be slightly higher than 0, then it might be 0.2 or 0.3 or something. And then so you take the highest ones in that row for that user, and you say, okay, you've read this one and this one, but these other ones are probably going to be the ones that you're interested in. Does that kind of make sense what it's doing? So the idea is that it's that you've learned some structure here, because there's much less information in these 2 matrices than there is in the original matrix, in theory. And so you've kind of compressed the information in here, and in doing that, you've kind of uncovered some latent structure in this. So you've kind of maybe perhaps identified some users that are similar and some articles that are similar, and that's what you've got described in these 2 factorizations, and that's what allows you to predict which other articles the user is going to be interested in. Okay, so that worked really well in our evaluation, but the problem for us was, okay, what if we have a new user now? So maybe we've already got a matrix like this, but how could we add another row on here for a new user, or add another column for a new article? And that was a problem that, as far as we could tell, hadn't been tackled. And we solved it with a very simple observation, which is essentially just that if I remove a row from here, if I remove a user, all I have to do is remove a corresponding row down here. And because these algorithms are essentially iterative, you can do the converse, right? So you can just add a row on here, put in the 1s and 0s, add another row down here, which you'll initialize randomly, and then perform a few more iterations, and you'll immediately be able to learn from the structure that you've already learned what the representation of this user should be down here. So that was the kind of key observation, but we kind of generalized that as well. So rather than just adding a single user, you could, instead of training on the whole matrix, you can take any subset of users you like. So perhaps the total number of users would be too big to fit in memory even. So just take a subset of, say, 1,000 users or 10,000 users and just train on that batch, or just perform some iterations on that batch. And once you've finished your iterations, you can then go back and update your big matrix with those iterations just for those users. That's the actual algorithm. I'm not going to go through it, don't worry, it's in the paper. Okay, so that was the idea. It was just something we thought of, but we had to make sure that it worked, right? And that's what these experiments are about. So this shows us, so I should have said the way we were evaluating it is measuring precision at 10, which means if I train on a training set and I've got some held out data in the test set, which are the articles that the user has read, and I recommend 10 articles to that user, how many of those 10 articles, or what proportion of those 10 articles are in the test set? I mean, average over users. And basically you can see that as long as your batch size is big, so for the times, as long as it's over 10, around about 10,000, there's no drop off in the accuracy and the precision at 10. And this curve will look different for every data set, so you'd have to do some kind of tuning for each data set. So that was really good. So then we can use this approach. We can have a matrix built, and then given some new users, we can just take 10,000 users out of that sample of maybe 100,000 users, take 10,000, perform some iterations, and update the matrix, and we can immediately recommend for those new users. Okay, the second question we asked was, okay, that's good. We can have these batches of users. What if we want to parallelize it? Because we were trying to build something that was very scalable. So the second experiment we did was looking at if you run these batches in parallel, does the precision at 10 degrade at some point? And basically what happens is if you've got these batches in parallel, some of those batches will have the same users in them, and you'll be updating and overwriting them, so it's not obvious that it's going to work, right? And at the extreme end here, what's happening is that in this particular data set, there's only enough for about 100 batches or something, so they're all overwriting each other, and there isn't a chance for them to interact and update. So that's why the performance down here is really bad. But as long as you're somewhere down here, say less than about 10 or 20 things in parallel, everything's good. So that was also a really good discovery. So that's pretty much the experiments and the algorithms. Any questions on that stuff? Okay, so how do we actually build this thing? We tried to use a kind of service-oriented architecture. It's not quite microservices, because some of these things, basically all these things talk to each other through Bigtable. So Bigtable is a huge database that Google provide. And the reason we use Bigtable is because it's got very low latency, so it's something like 6 milliseconds to retrieve something, which allowed us to do very fast, to recommend things very quickly. And each of these is a kind of a service that's living in a Kubernetes, Anyone familiar with Kubernetes? Cool. So Kubernetes is a service for kind of managing lots of different applications that run on Docker instances. Anyone familiar with Docker? Similar people. So, basically, Docker is like a lightweight. Docker instance is kind of like a lightweight VM, but yeah, I won't go into the details of that. Basically, Kubernetes allows us to have lots of things running. We can easily scale up and scale down the number of instances we have of something. So if we wanted to run more of these batches in parallel, we could easily just deploy more instances of something. And the kind of flow we had was a user comes and reads something at the Times or the Sun. We then send a message. So we're using Google PubSub to handle the flow of messages. So we send a message that comes in here to say, okay, this user's read something. We then store that message in Bigtable. We also send a message to the model builders here to say, this user's read something new, so we need to update their model. And then each of these model builders will then try and update the model for that user. And when the model's built, it stores it in Bigtable again. And then we have these serving APIs that when a user requests recommendations through the API, it'll either be routed to one of these three APIs. So we have the content-based recommendations, the collaborative recommendations, or just the most popular articles. If we don't know anything about the user, so the first time a user visits, we won't know anything about them, we won't be able to give them personalised recommendations, so we just give them the top articles. And what this does is it pulls the model out of Bigtable. In the case of the content, it's the logistic regression model, so it's just a vector essentially and a bias that we pull out. And we rank the articles, so the articles will generally be cached. So vectors for articles will generally be cached in memory. If not, we have to go back to Bigtable and get those as well. And then we rank them and return them back to the user. In the case of the collaborative model, the model relating to a user is just their row in that matrix. So the matrix is stored in kind of a distributed way. So we just store each of the rows for each user separately. And at serving time, we just put out the row for that user. And again, rank the articles and return the top ones. Yeah.
Can I ask a question? So you said if you have a user reads a new article, right, you need to update that user.
Yes.
You said you took a sample, so would that update everyone else in the sample as well? Or
It
would
would.
just update that user?
Yes. So because we need this batch of 10,000, if we didn't have, so we've got these messages coming in, we read a batch of messages, so there might be 10 or 20 people in that batch. So if we don't have enough people in the batch, which we generally don't, we put out an extra 9,990 users or whatever to fill that batch up to 10,000, which those are just chosen at random. And yeah, we then update all of those users' vectors as well. It's a good question whether we need to or not. I think we probably do. But yeah. Any other questions on the architecture? It's my last slide, so feel free to. Or should we just go on to the conclusion?
It's just a thought. You said you took people at random. Did you not did you weight it by people that have been had the longest time since they were updated, essentially, or try and just I don't know if it would help stop anyone going stale in that matrix?
Yeah, we could do. I mean, the thing is, because we have new messages coming in all the time, and our user base is larger, but it's not that large. So eventually, you will cover all the users. Yeah, I suppose something like that might be worthwhile. What we do is data that gets very old, we just delete anyway. So after 6 months, we just delete data. So that helps us with users that are completely inactive. Okay, so I'll conclude quickly and then have more questions if necessary. So basically, hopefully I've convinced you that matrix factorization is useful. If you want to do it recommendations quickly, then you can do that. You just do it in batches, and you can parallelize batches. That's pretty much it. Thank you very much.
Thank you very much.